Alright guys, let's go ahead and get started with these notes about how to calculate energy. So first thing we want to talk about is the fact that we understand the types of energy and how it is transferred. But now we want to know how to make these calculations, because we know that energy cannot be created nor destroyed, only transferred from one form to another. And remember those types of energy that we talked about were gravitational potential energy, kinetic energy, elastic potential energy, and thermal energy. So just a quick refresher, energy is always measured in joules. Perfect. Let's move on to the next slide. Number 1, equations. So let's talk about the equation for gravitational potential energy, or sometimes referred to as GPE. So our equation is going to be GPE equals m times g times h. And m stands for mass, g is going to stand for gravity, and we know that gravity on Earth is 9.8, and h is going to mean height. So looking at our equation, we can see that as mass increases, or the more mass we have, the more gravitational potential energy we are going to have. Another thing we can notice is that as height increases, so the more height we have, the more gravitational potential energy we will also have. Now let's take a look at kinetic energy. Kinetic energy is equal to 1/2 times m times v squared. And again, m just stands for mass, and v stands for velocity. So if we ask ourselves if kinetic energy can ever be negative, we would have to look at the two variables that it depends on. It depends on mass and velocity. Well, mass can never be negative, and velocity could be negative or positive. But since we can see that velocity is squared in our equation right here, that's going to mean that even if velocity was negative, a negative squared gives us a positive. So therefore, kinetic energy can never be negative. Next slide is our first practice problem. Here in this problem, we have a guy named Rich. He's about 70 kilograms, and he is falling off the roof of his garage, which is about 3 meters high, and he wants to do some sort of awesome stunt. Assume as Rich falls that we can ignore air resistance. So when we say that we're ignoring air resistance, that just means that we will not have any thermal energy in this problem. We want to identify the system and then draw energy pie charts at the beginning and the end of his motion. So the system is going to be our person, in this case Rich, the earth, gravity, and the garage. And again, the system is just what pieces of information are important in this problem and may play a role in the amount of energy that we have. Rich is important because he has mass, and that's going to play a role. The earth is important because of its gravity. And lastly, the garage is important because it has height. So let's go ahead and draw that energy pie chart for the beginning. And if we think about it, we have Rich starting on the roof of his garage 3 meters above the ground. Therefore, we should have an energy pie chart that has a lot of energy that depends on height. Well, that's going to be gravitational potential energy. Rich is not moving on the top of his garage, so there's no other energies present. Next, we have his energy at the bottom, and at the bottom is going to be when he hits the ground. In other words, when his height is 0. Therefore, our total energy at the end is all going to be transferred into kinetic energy. And again, the reason being is that at the ground, there's no height, and there's also no thermal energy, which is taking up any of the energy. So we're just left with all kinetic energy, because at the ground, he is moving when he hits that ground. So let's work through this and actually calculate what those energies are. Since we have height and mass, we can go ahead and calculate the GPE first. We know that GPE is equal to mass times gravity times height. If I look at my equation, the 70 kilograms right here is the mass, the 9.8 is my gravity, and the 3 is my height. I'm just going to go ahead and multiply all these together, and doing so gives me a gravitational potential energy of 2058 joules. Since our GPE is our only energy that we're starting with, that's going to be our total energy. So in this case, our GPE is equal to the total. And again, that's only the case because GPE is the only energy that we start with. If we started with more than one energy, we would just have to add those up to get our total. Next, we can know that the law of conservation of energy tells us that energy cannot be created or destroyed. So whatever energy we start with is going to be the same energy that we end with. And since we know that in the beginning, Rich has all GPE, and in the end, he has all KE, we can take all of that GPE in the beginning, 2058, which is our total, and transfer it all into kinetic energy at the end.
We should take Bikini Bottom and push it somewhere else!
Meaning that at the end, we have a kinetic energy of 2058 joules. So let's go ahead and fill out our table. We have GPE is equal to 2058 joules in the beginning, and kinetic energy is 0 joules in the beginning because Rich is at rest before he jumps off his garage. The total energy is us adding those two together. The total energy at the end is the same as the beginning. And then the energies at the end, we know that GPE is now 0 because we don't have any height, and KE is now 2058 joules. Again, that's because all of that gravitational potential energy was transferred into kinetic energy. And the reason I know that is because energy cannot be created or destroyed, only transferred. So now let's take a look at calculating Rich's velocity as he hits the ground. Well, if we're talking about velocity, we're going to need the kinetic energy equation. And that tells us that kinetic energy is equal to 1/2 mv squared. We know our mass and we know kinetic energy, so we can plug that in. Kinetic energy is 2058, 1/2 is 1/2, m is 70, and v is unknown. So we can simplify by multiplying 1/2 times 70, we get 35, and then next, we'll go ahead and get v by itself by dividing 2058 by 35. Once we do that, we're just left with 58.8 equals v squared. Go ahead and square root both sides, and we find out that the velocity of Rich when he reaches the ground should be 7.67 meters per second. All right, so now let's take a look at the same problem, but this time we're going to include air resistance, and that air resistance is going to be 1000 joules. So let's identify the system just like we did before. We're going to see that we have the person, earth, gravity, and the garage, just like we did before. And next, we're going to go ahead and draw these pie charts. So in the beginning, Rich is still on top of his garage. He has not moved, so all he has is gravitational potential energy. In the end, though, he has fallen through the air, so he has lost some energy to air resistance. And that energy has gone into thermal energy. So in the end, we no longer have all of KE, we have a part of KE and a part of thermal energy. Again, I don't know exactly what the ratio is, but I'm just going to guesstimate on my pie chart like I did below. If it was half, then I would put half. I know it's less than half though, but because I don't know the exact amount, it's fine to just estimate how big each portion of your pie chart is, like I did below. Another thing I want to mention about this is that thermal energy will only be present in the end of our energy pie charts. We cannot start with thermal energy because thermal energy is energy that is lost. We can't lose something if we haven't started. So thermal energy will only be present in the end. All right, so let's go ahead and calculate all the energy that's present. We got GPE again in the beginning, and we know that GPE is just going to be the same that it was before because we have the same mass, the same gravity, and the same height. That's going to give us 2058 joules, just like before. What's different though is the KE. We can see in our energy pie chart above that we don't have the same amount of KE as before. We have lost some of that due to thermal energy. And the way we're going to figure that out is by taking our total energy which is still 2058 joules because that came from GPE in the beginning, and transferring that over to the end. From that, though, we know that we are going to lose 1,000 of those joules to thermal energy. So we are going to subtract 1,000 from 2058 joules, and that will give us our kinetic energy. In other words, our total energy is going to be equal to all of those energies added up. We know that the total equals 2058, so we're going to plug that in and have 2058 equal kinetic energy plus thermal energy. If we want to solve for kinetic energy, we're just going to subtract the thermal energy over to the other side. That's going to give us a kinetic energy of 1058 joules. If you want to double check, you can just plug kinetic back into the equation, add thermal to it, and make sure that your total at the end is equal to your total in the beginning. So here's our chart, just like before. Let's just go ahead and fill it out real quick. The total amount of energy of each of the different types. In the beginning, we have GPE, which is 2058 joules, 0 kinetic because we're not moving, and 0 thermal because we have not lost any energy yet. Our total is us adding all those up. Total at the end is the same as total in the beginning, which is 2058 joules. And then we just calculated these. Our kinetic energy at the end was 1058 joules, and that's because we lost 1000 joules to thermal energy. If we want to figure out the velocity at the end, we're just going to do exactly what we did before, where we take our kinetic energy equation and then plug in our values from before. So 1058 is our kinetic energy, 70 is our mass, and then we're going to solve for V just like we did before. Go ahead and simplify, and we find out that V is equal to 5.49 meters per second. And this makes sense because we would expect our velocity to be less than it was in our previous problem. And it's going to be less because we lost some of that energy due to thermal. And also it's going to be less because the air resistance is going to slow us down. Hence resistance, right? It's going to resist our motion and make it so we move slower. All right, so let's review what we just talked about. We said that GPE depends on mass, height, and gravity. What does that mean? That means that as mass increases, we're going to have more GPE. And as height increases, we're going to have more GPE. Another thing this means is that on different planets, we're going to have different gravitational potential energies because different planets have different gravity. The next thing I want to talk about is kinetic energy. And kinetic energy depends on mass and velocity. That means that as mass increases, our kinetic energy increases. And as velocity increases, kinetic energy is also going to increase. Something important to note, though, is that velocity in our kinetic energy equation is squared. So if we actually double the velocity, it will end up quadrupling the kinetic energy. So whatever you do to velocity, it's going to have a squared result on kinetic energy. Last is how thermal energy depends on air resistance and friction, and then our total energy is the same before as it is after, because energy will always stay the same. So whatever we start with is the same that we are going to end with.